I would like to introduce Dr. Adrian Grantham today, and he's from the University of South Australia. And Adrian has just completed his PhD with a good colleague of mine in applied mathematics. His thesis title was Mathematical Tools for Maximising Renewable Energy Use in Electricity Supply. His research interests include time series analysis, probabilistic forecasting, battery storage, and anything else related to the utilisation of renewable energy. So let's welcome Adrian. Thank you.
Well, thanks everyone. So, as Melinda said, I've just finished my PhD, and today I'm going to talk about a couple of my chapters, but with a stronger emphasis on probabilistic forecasting of solar radiation. So I should do some acknowledgements first. The Australian Mathematical Society and my university helped pay for me to come today, and also acknowledge some of the collaborators that I've been working on in this area. Professor John Bolland, who was my principal supervisor, and a friend of his, Associate Professor Yulia Gell, who's at the University of Texas. So, motivation, with a couple of conversations that I've had this morning, I think this is pretty obvious. If we're going to be supplying energy into the electricity grid, it's important to know how much of the expected output from renewable energies, particularly large-scale PV and CS, concentrating solar thermal in this case. And I think it's coincidental that I've been working on this, and there's been some recent announcements in the last few months about these large-scale solar PV systems and large-scale concentrating solar thermal quite close to my hometown in Port Augusta, which is in South Australia. So I think that's, you know, a bit of a wraparound there. But traditionally, people just do point forecasts, which is just that the output is going to be this. We think that it is far more valuable if you're able to give a probabilistic forecast. So what we kind of do is that we provide with, you know, some error bounds around a forecast of some kind of confidence. And being able to do that allows us to make better informed decisions, because we are in effect being able to quantify risk. And some places may want, you know, there might be circumstances where they want to take a risk or they don't. So that would probably depend on their business model there. So our broad approach to doing probabilistic forecasting of solar radiation is first, develop a point forecast. From there you'll get some errors. And then we take those errors and then we use that to develop our probabilistic forecasting method. Now I'd point out that from a probabilistic point of view, you could kind of bring, with our method, you can bring your own point forecast as long as it's got errors, which they all do. Our technique for the probabilistic component is still can still be applied. So for today's talk, I'm first of all going to talk about our first approach to this. So our first approach to point forecasting, which I've called P1, it's quite original, and our first approach to probabilistic forecasting. Now I can't call it P1 again, unfortunately, even though I wanted to. So because it's kind of like interval forecasting or prediction intervals, we decided to call it, we'll denote it with I as well. So P1, I1 is our first approach, P2, I2 is our second approach. And there I've used them as sort of placeholders in the slides to try and help navigate us through. But if anyone gets confused, please yell out and I'll just remind us what's going on. So I'm going to describe those methods, and then I'm going to just show you the results that we get. And then at the end, I'll show you something that is something else that we're able to do with our point forecast, which is quite valuable. And this is some new work that I don't think too many people in the world are working on, certainly with respect to renewables. I think it's more done in the sort of the finance sector. So we had access to 10 years of data from 3 locations in South Australia. Two of them were in South Australia, Adelaide, Darwin and Mildura. Now we chose those 3 because they have 3 distinct climate types, and that allows us to be able to test the robustness of our method against different kinds of climate. So the first thing we do is that we develop our point forecasting model. Now we take a statistical approach to doing this, and what we do is that we first, so our point forecasting is made up of, say, three components. It's the Fourier component, the FT that you see up there. That so we use a bunch of trigonometric functions to be able to explain what the climate is doing. Okay. Once we take care of the climate aspect of solar radiation, we then use armour modelling to see if there is any serial correlation left in those residuals after we take the Fourier component out. And then the last bit is obviously our errors. Now the errors may be heteroscedastic, so there is a changing variance in time. Ideally we want them to be constant throughout time. It makes our life easier, but they're not now. This is an important point that we will touch upon a little bit later on. So in order to do Fourier analysis, we have to identify what are the frequencies that we're going to use. So we do power spectrum analysis on our hourly global solar irradiation, and we identify 11 frequencies. Now they are once a year, so we're taking into that, summer is different to winter, twice a year, because autumn is different to spring. Then we have once a day, twice a day, and 3 times a day. And for the daily cycles, we also have side bands. And that are these things that are identified just on the opposite side. So here we have once a day because we're down at 365, so it's once every 365 days. But we have the little spikes on either side of that. They're called side bands, and they allow us to modulate the amplitude to suit the time of year. There's some other frequencies at the end that the slide wouldn't show, but just be mindful that they're there. So we're now able to model, as I said, the climate in effect. We have our Fourier model there, and we're able to explain depending on the location, between 80 and 85% of the variance, which is a fair swagger, I think. I know it's nowhere near that for wind, but 80 to 85%, just by doing that alone, I think was pretty impressive. Now we just plot what our Fourier, if we were just to do our Fourier modelling, what that looks like. So on the left here, we have, I think in blue, is our observed, looks like a nice clear sky, and the dotted red is the Fourier component. On the right here, we have a cloudy day, and as we can see, the Fourier is picking up the climate for that day because it's kind of like the average, but it's not doing a very good job at picking up those pesky clouds. From a solar forecasting point of view, I wish there weren't clouds, okay? That would make life a lot easier, but we have to deal with them. So what are we going to do about them? Well, our next approach is to use armour modelling. So this is where we take the residuals that we have when we take away the Fourier component from our observed. So here we have a particle autocorrelation function that is slowly decaying. And then we have the partial autocorrelation, which shows that we have some significant spikes at lag 1 and lag 2. That means that what is happening at the previous time step and even the time step before that is having a bit of an influence on what's going on now. Okay? So that's what we talk about when we're talking about serial correlation. So that suggests that we have an autoregressive model of order 2 for 2 steps behind. So we fitted that, but a technique that we use is that we overfit it. So what we did is okay, even though that graph says we should only go to 2 legs, let's try overfitting it and going to 3. And that gave us a slight improvement. So we ended up going with an AR3. It's just a good lesson to know that just don't look at data or even look at the graph and make decisions. Play around with it and see what else you can discover. So now we have those same 2 days, our clear sky on the right, on the left, which we've been able to improve slightly. And where we have our cloudy day on the right, we're able to see that we are able to capture a bit more of the transient effect of clouds. Now, the differences that we have between what we're being able to model and this is what we're building up our deterministic component, and actually what is observed is our final errors, our ZTs. So we take them and then we work on towards doing a probabilistic forecast. So we had this idea that the heteroscedasticity of those errors might be driven by a sun position, that is elevation and azimuth. Well, in this case, it's elevation and sun hour angle, they're the same kind of thing. So we placed our hourly errors into a two-dimensional binning structure, kind of like what we see there, which is driven by the time of day, time of year, which obviously corresponds to our sun hour angle and our sun elevation. So for example, this little bin here, sort of in the middle down the low, that's sort of around the middle of the day in winter when the sun is in that position. So whenever we are, so we've generated a model, we've got an error. If that error corresponds to that time, so that combination of sun hour angle and sun elevation, we put them in that bin. So we go through all of our 8 years of our training data, and anytime we're in that particular quadrant, we put all of our errors in there, okay? So that was sort of an idea that we had. And as I said, that the variance is systematically changes throughout the time of year. And what I then did is I plotted a little histogram of the distributions for each one of those sun positions, and none of those, well, you might get the odd distribution that looks similar, but it just highlights that we do have changing variance. So we've got all of our errors in our bins. How do we do a probabilistic forecast? So we say we're at that midday winter time. I've got my point forecast. I then go to the corresponding bin that particular time corresponds to, which contains all of those errors for that particular sun position. And if I'm interested in constructing a 95% prediction interval, I will grab the lower 2.5 percentile and the upper 97.5 percentile, and then I will add that to my point forecast, and that'll give me an upper and lower prediction interval. And we just go through time generating our prediction intervals like that. So that was, as I said, our first approach to point forecasting and our first approach to our probabilistic forecasting. And so we've got a paper out about that. But like everything, we think we can do better. Well, let's hope so. So since that paper's been published, we've been able to work on a new point forecast and a new probabilistic forecasting method as well. So with the point forecast, I'll explain what this graph is. This shows you kind of which approach is best for point forecasting for various combinations of forecast time horizon and spatial distance. So we're in the hourly, and we're using a statistical approach. So that's kind of good that the statistical approach is in one of the better performing point forecasts for that time horizon. But we had this idea that if we knew what was going to happen, if we had a forecast that say a day ahead, we might be able to do something with our hourly forecast. I.e., if we know that it's going to be very cloudy tomorrow or later this afternoon, we might be able to start thinking about that with our point forecast. So we had this idea that we would combine a numerical weather prediction forecast for a day ahead, which are known to be one of the better performing forecasts, with our statistical approach to an hourly forecast. So that's our idea, that we kind of merge those two together. And I do apologise for all the text here, but what we actually did, we didn't cheat, but we didn't have numerical weather prediction data at the time. So we used perfect knowledge of the day ahead as a proxy. Now, we're never ever going to know we're never ever going to have perfect knowledge of the day ahead. But we thought this would be a good idea to at least demonstrate that this idea might work if we did have it, which I'll point out that we have just, I think, in the last few weeks had access to it, but not when we were doing this work. So that's our idea. We'll use perfect knowledge of the day ahead to try and see if we can improve our hourly. So what we did is that I know that tomorrow is going to have this amount of solar resource. We, what I call, bend our Fourier component to match that daily. So what that kind of means is, so I have a time series of 24 Fourier components for the day ahead. And we're going to incorporate a day ahead forecast. As I said, our perfect knowledge is our proxy for, hopefully down the track, an NWP. So if the NWP is going to target, say, 5,000 watt hours per square metre, we will scale our Fourier component to make sure it hits that. Okay? That's kind of the best way to describe that. And there's some results that I'll show towards the end that sort of suggest that that is a good idea. So that's what we do. We try to incorporate knowledge of our day ahead with our hourly to try and see if we can do better. So now this comes to our second method of probabilistic forecasting. So as a reminder, our first approach, we just took a very systematic approach to the variation in variance. I kind of refer to it as more of a global approach to it. However, what we've done this time is that we're still going to do that, but we're going to introduce a conditional heteroscedastic approach to it. That is, well, if the variance in solar radiation has been quite small in the last, say, few hours, maybe it's going to be small in the up and coming hours. Okay. Whereas before we didn't quite do that. We were just going, well, what's the kind of the variance at this, time, more of a globally view of, this particular sun position. So the areas are uncorrelated, but they are dependent. The squared terms, which is a proxy for the variance, are correlated. And this is called the arch effect. The autoregressive conditional heteroscedastic. Which I must admit is a mouthful to be able to say. So usually when this happens, we look at using an arch technique or a gauge technique to being able to forecast that variance. But we found that exponentially smoothing form was more useful. But since we're going to be forecasting the variance and then constructing prediction intervals using this, we have to perform this assuming that the errors are normally distributed, which they aren't. So, and now a lot of people would just go, well, let's just assume they are anyway. And they just keep going on with an arch or a gauge. And they get some results. But we didn't do that because they're not. So we thought we would try a normalizing transformation technique to be able to do this for us, to be able to take care of that. So there's a few steps here, so please bear with me. So we have an error for we're at time t. We want to forecast, probabilistic forecast for time t plus 1. We take our error that we're currently at. We then go to our bin, for that time, for that sun position, and we calculate what percentile that error is. So let's just say it's the 50 percentile. Okay, we know the percentile. Then we convert that to a Z value for the standard normal distribution. So the 50th percentile, for example, for the standard normal distribution is 0. So we're now getting a Z value. Then because we've got our Z value, and at this point we're in a normal distribution, so that's okay. We then use our exponential smoothing. So that's kind of like a memory. We're going to use a fair bit of what's going on in the previous time step, or in this case the current time step, to be able to help us predict what's going to happen on in the next time step. And then from there we can generate our prediction intervals by, you know, if we're interested in a 95% prediction interval, we're going to take that Z value and times it by 1.96 plus or minus to give us some, 95% prediction intervals. But the key thing here is that we're still in a standard normal distribution. We have to transform it back. So once we've transformed it back, just kind of going in the opposite direction, we now have conditionally heteroscedastic error bounds for, well, you know, two values, an upper and a lower for our errors, and then we just add it again to our point forecast, and we get an upper and lower prediction interval. Whereas so it's like before, we're still using that, the systematic change in variance, that global approach to the way our errors are changing, but we're also incorporating that conditional aspect of it, of kind of, well, what's going on now though? You know, is there a lot of variance going on now or not so little? So now I'll just give you a quick overview of our results. So this is now looking at our point forecast when we're looking at the normalised root mean square error. So here we have our original, and then if we incorporate our day ahead, as you can see, those numbers get smaller, which means we're getting better, okay, for all three locations. Here we have our mean bias error, and once again we're getting better results with knowing day ahead. And our mean absolute error numbers are smaller again. Now, it's not surprising because, as I said, we were using known day ahead. Now, it was perfect knowledge. But we're thinking that, well, we have certainly demonstrated that it is an improvement. And because a numerical weather prediction is better on that day ahead sort of time scale, it sort of demonstrates to us that it's worth pursuing this, incorporating a numerical weather prediction approach. So we'll probably get our new error measures once we do that, will probably fall in between. But let's hope, well, I hope they fall in between, closer to the P2 values. So now we'll have a look at the performance measures that we can use to determine, have we got a good prediction interval? Is our probabilistic forecast behaving? So one of them, there's a few of them. The first one is coverage. Now coverage is simply the percentage of observations that actually do fall within your prediction intervals, within your probabilistic forecast. So if you're generating a probabilistic forecast with 95% prediction intervals, you are expecting 95% of your values to fall within those prediction intervals. That's your target. If you're setting up your probabilistic forecast with 99% prediction intervals, you would expect 99%. You'd want 99% coverage. That is, 99% of your values are going to fall within those prediction intervals. Now that is for a well-calibrated forecast. So that's kind of what we're aiming for. And look, and the reason why you're not going to get it right all the time is sometimes you're going to be wrong, right? So, because we are measuring the probability, we're taking, we are quantifying the risk. So we will get it wrong sometimes. But because coverage is easy to obtain, if I just want coverage, I'll just make the intervals wider, right? But is it really good for me to say, oh, tomorrow's temperature is going to be between 0 and 40 for Sydney? I reckon I'm going to be right. But is that useful? Or would it be more useful if I said it's going to be between, I don't know what the forecast is, but let's just say it's going to be between 18 and 22. That's far more informative, isn't it? So what you're aiming for is that you want to be calibrated, that is, you're getting the coverage that you're targeting, but you want the narrowest widths possible. So there is also this coverage width base criterion, which kind of quantifies the trade-off between the two. Yeah, sure, if I want better coverage, I can just make my prediction intervals wider, but I don't want wide intervals, I want narrow intervals, but then that might be affecting my coverage. So this, the coverage width-based criterion kind of quantifies what, the trade-off between those two. However, this is a well-used metric in the literature, but because they have this little condition here, in other words, are we under coverage or over coverage, they don't penalise them the same way, which we don't agree with. In my view, if you are aiming for a 95% coverage, what's the difference between 94.5 and 95.5? You're 5% out. So we just do a slight change to that where we try to penalise both ways the same. And here we have some results. So along the x-axis we have our nominal coverage. That's the coverage that we're trying to get. Along the y-axis here we have our CWC metric. So the key thing here is that the lower the better. Okay. So this is for Adelaide. So there's two things to note, that the blue markers are always lower, which means that it's better. Now the blue stands is for our second version of our point forecast, which is not surprising because we got better results for our point forecast. So that's good. It's what we were expecting, and it's always pleasant that what you get and what you expect is also good. Now you'll also note that if we kind of ignore the colours for the moment, that the squares relative to their colour component are better, give a better CWC than the stars. So that means, so that's basically saying that our second approach to our probabilistic forecast is better than our original approach. And we got, so that was encouraging, our point forecasters, we're getting better results with our new probabilistic forecast. That's for Adelaide. And also similar for Mildura. But for Darwin, given its tropical climate, it's not quite the same. Our second version of our probabilistic forecast isn't quite doing as good a job as we were hoping, and certainly not as it did for Adelaide and Mildura. Here we have some examples of what these forecasts look like, okay? So the blue, so here we have a clear sky in Adelaide, and the blue is actually what was observed. The red dashed is our 95% prediction interval for our second approach, and the green is for our first approach. So you can see, like, for a clear sky, we are really able to get the same coverage, but our widths were a lot smaller. Okay? And I think that kind of makes sense, because on a clear sky day, remember we're now incorporating a conditional variance aspect to it. Well, it's not, the variance isn't changing much. And that's what we keep thinking, well, it wasn't changing much now, so we suspect it's not going to change much in the next time step. Bit mixed for when we get a sort of a cloudy day. I'd say sort of my take home is that definitely for all clear sky days, our second approach for Adelaide is better. On the cloudy days, it's mixed. But overall, it's pretty good because we don't always have cloudy days. We do get some, well, quite a few clear sky days. For Darwin, I categorise this as a clear sky. It looks reasonably clear. Once again, because it's clearish, we're able to, our new approach in the red is doing able to get us our narrower prediction intervals than the green dashed, which was our previous go. But here we have a bit more of a cloudy day. We can see that our old method is performing better. So our results are mixed. Certainly for Adelaide and Mildura, our second probabilistic forecast method is doing better. Not so good for, I can't say the same for Darwin. So I think that the take home here is that maybe our approach might be dependent on the climate. And some more testing of various other locations might help us to determine that. But maybe for those tropical locations like Darwin, our first approach is better. And we've also looked at even maybe combining those two methods. So can we have another level of smarts into our forecast that goes, and maybe this is where the NWP will really be useful. Hey, if the NWP suggests that it's a clear sky, well, we'll go with that probabilistic method that has shown that that is better for clear skies. If our NWP suggests that it's going to be quite cloudy, well, then maybe we'll try that other method. And maybe that's a smart way of being able to switch between the two. That's what we're hoping. So there's certainly some more work to come out of that with incorporating a numerical weather prediction. Okay, so that kind of covers what I wanted to talk about of probabilistic forecasting. So now I'm going to talk about something else that we were able to do, the other chapter of my PhD, which is called synthetic sequences of solar radiation, or global horizontal irradiance, which is what that GHI stands for. So if you recall our point forecast, this was our model for our point forecast. I like to be able to get as much bang for my work as possible. So we thought we can use this again, but in a slightly different way. Instead of generating a probabilistic forecast, we can generate synthetic sequences. Now, before I go to that, I won't scare you with that yet. What do we mean by synthetic sequence? Now, in the literature, a lot of people think of synthetic sequences. They use it to denote when you are maybe downscaling from hourly to minute, kind of like interpolating, because high frequency data is not very readily available. A lot of people are working in that space, even us for that matter. But what we mean is, what was the motivation here is that we tend to not have long periods of historical data. Maybe 10 years, maybe 20, I think might be some of the better ones, or even worse, a typical meteorological year. But just because we've only observed, say, a sequence of solar radiation doesn't mean to say that it's not going to happen. So we generated, I think it was like 1,000 synthetic years worth of data, where those synthetic data still had the same statistical properties as our real. So any event was equally as likely to occur, but because we generated 1,000 years, we might be able to find a sequence that, as I said, is as equally as likely to occur, but we just haven't seen it yet in the observed. So that's the formula. It's very similar to before. The only difference is that whereas with our point forecast, our autoregressive component is calculated on the errors that are generated from past observed values. Whereas this time, there's no such thing as an observed value. We generate it on past errors from our synthetic value. Okay, so Another way to kind of make that distinction is I might generate a synthetic value for January 1st at 12 o'clock, but it has no concept of year. The synthetic values that I generate at that time point will have the same statistical properties as the observed for that time point, but this one doesn't, it's not like it doesn't correspond to a year. So once again, I think that kind of summarises what I said before. The hourly distributions in our synthetics is the same as our reals. The serial correlation in our synthetics has the same serial structure as the observed, and the same on the daily scale as well. So I don't know how well that's going to show up, but here we have 5 synthetic sequences for daily GHI for the month of January. I didn't bother plotting all 1,000 of them. I don't know whether that would have been of any use, but we certainly see that we're getting different sequences. Now we might not have seen some of them in the real data, but they're as equally as likely to occur. We just haven't seen them yet. Same for our hourly. We're getting some clear sky days through here, and we're also getting some cloudy days as well. So what's the value of this? Well, just to say, for example, you're designing a large-scale PV system with may or may not have battery, but as part of your design process, you're interested in what's the number of consecutive days that there are less than 2,000 watt hours per square metre. Maybe that's how much storage you're going to size up to be able to get you through the night. It's a hypothetical situation. Well, if we have a look at the observed, we see that the longest streak under that condition was 5. And that sort of occurred 12.5 times in a 100-year event. Okay? So you might go, bang, I don't see anything more than that. I'm going to design it to be able to survive for 5 days. However, with our synthetics, our 1,000 years, we can pass that through to be able to test the performance of our system. Now, remember that these have the exact same statistical properties as our observed, but they just may contain sequences. Well, we've got 1,000 years. There's going to be more sequences in there than, say, in this case it was 8 or 10 years, I can't recall. And we see that, in fact, our longest sequence was 9 days. And admittedly, it was a very small occurrence. It was 0.1 in a 100-year event. But we're also seeing sequences of 6, 7 and 8. So this kind of shows you the value of what synthetics can tell you. It allows you to design your system more robustly. That's again summarising kind of what I've said before, but maybe I'll just remind you. So the synthetic data can easily be used, for example, as testing the performance of the operation of a solar energy system for all supply scenarios, not just those that we've observed, okay? Now this is part of a bigger work where we're going to then let's generate synthetic seasons first, then generate synthetic days, synthetic hours, synthetic minutes, and use them all in a chain to be able to generate synthetic data at higher frequency. And I think that's all, which I think we've just got enough time. Yeah. Any questions, comments? Yes.
Alright, so with regards to your synthetic sequence here at the end, have you tested it against like other pre-existing algorithms, like the Markov chains that already exist, say like medianal?
Yeah, like the literature tends to use Markov chains to be able to do that downscaling, which is not what we're doing at all.
Well, so say like
yes,
medianal, for instance, use Markov chains to generate the daily sequence, like completely from random number generators and tables, and then they go down and step it to the hourly.
Yes,
and in the
you
most
could do
recent
that, but
version
we've taken more of a statistical approach to it.
Yeah, so I'm asking, have you looked at how the numbers stack up from your method versus, say, pre-existing algorithms?
No, we haven't done that comparison. Not too many people are doing what I refer to as synthetic sequences. There's one paper out there that does do it, but they look at I think cloud cover for within their Markov chain as a sort of.
Yeah, well, I'm just saying this because, like, in industry, synthetic weather is actually used quite heavily. So, for instance, synthetic weather is done by Meteonorm and it's implemented in PVSys, and a lot of people use PVSys. So if they don't have a TMY or they don't have a weather file, they actually use synthetic weather already.
I'll have to talk to you after then about that because I'm not aware of it. There are some subtleties that might need to be discovered about that. Thank you. Oh. Yeah.
Okay, my question is, your second model is more likely depend on the day-ahead forecasting. So usually, as a common knowledge, day-ahead forecasting is not as good as hour-ahead forecasting. So
Yes.
if your model is heavily depend on the day-ahead forecasting, but in the real life, the day-ahead forecasting is not that accurate. So what?
Well, we're merging the two together. Okay, how are we going to do that? We're not sure about yet, but that's with the NWP. But with what we did with the perfect knowledge is as we just bent our Fourier to actually fit. Now, the Fourier explains is a fair contributor to our model. Now remember that the Fourier is doing the climate, so it's kind of going, I'm expecting an average day, and then the autoregressive kind of tries to capture the difference between that. So I think while there is a bigger error on the daily, it gives us a better something maybe better to target than say what the average would be for that particular day of the year.
So quite depend on the average value of the day-ahead forecasting.
Well, that's kind of what the Fourier does. The Fourier is just like an average of that time of year. And then the autoregressive is just trying to pick up the deviations from that. If we can get a better idea of what, as I said, we bend that Fourier. If we can kind of get that in a better ballpark, because it's going to be really cloudy, we're going to lower its expectations a bit, then we might be able to do better with our hourly. So we haven't quite, we've done it with the perfect knowledge and that has seemed to be successful. We are yet to do it with the NWP. Maybe the errors are too much where we can't kind of get it to work. We could also, with our perfect knowledge, we were going to try to, well, as I said, that's ridiculous because we're never going to know it. We were going to try and perturb it, but we thought we'd at least go for this because this is kind of like, well, this is the best you can do. And then around that time, I think we were like, oh, we're going to get access to NWP. So that's kind of what we're trying to do. Haven't done it yet. Maybe it's not going to work out like we think.
It seems that there is class after us. So if there is more question, maybe we can take it outside. But let's take Adrian again for great talk.
Thank you.